How Newton could decipher gravity was adequate to allow us to fly from the Earth to the Moon anytime. Get yourself lost in the ticking hands of time, considering whether and how we could decipher it. This is basically the tip of the transient ice shelf on its head. His disclosure isn't just speculation. A key could open the approaches to the privileged insights of the universe, uncovering a reality more capricious and inspiring than we ever contemplated. Imagining how Brian Cox's new theory challenges our customary comprehension of time and the likely implications for our perception of reality. Join us on a captivating examination through the chronicles of time itself. We delve into Brian Cox's recently uncovered, wonderful speculation on the nature of time in the vast universe around us. Mysteries are ready to be unveiled, and some of these secrets involve confounding phenomena like time and gravity, which are key pieces of our existence. Envision a reality where time acts strangely, where it can either be slowed down or sped up. Furthermore, the force that keeps us grounded may not be what it seems. This is the domain of Albert Einstein's theories of relativity, which reveal how our interpretation of time and gravity diverges in unexpected ways. Albert Einstein, a name synonymous with groundbreaking discoveries, provided us with a superior perspective on the universe through his theories of relativity. His work laid the foundation for understanding how time behaves under different conditions, especially when traveling at incredible speeds. It all began in the early 20th century when Einstein proposed two pivotal theories: the special theory of relativity, 1905, and the general theory of relativity, 1915. The special theory of relativity, published in 1905, transformed our understanding of existence. Simply put, it tells us that the laws of physics remain the same for all observers who are not accelerating, regardless of their motion. This theory introduces the possibility of relativistic effects, including the well-known idea that time can stretch or slow down under certain conditions. One famous thought experiment to explain time dilation involves a light clock. Imagine being inside a spaceship traveling at an incredibly fast speed, almost at the speed of light. Inside the spaceship, a beam of light bounces between two mirrors, perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers. Therefore, the light beam appears to travel a diagonal path. Here's the fascinating part. The time it takes for the light beam to complete its journey should be the same for both the observer inside the spaceship and the one outside. However, because the path is longer for the external observer, it appears to take more time for the light to complete its excursion. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. Understanding how things change when they move fast, known as relativistic effects, isn't just theoretical. Scientists use massive machines, such as particle accelerators like the Large Hadron Collider, to make particles travel nearly at the speed of light. When things move this fast, we need to think of time differently to make accurate predictions and measurements. Einstein's special theory of relativity challenges our conventional understanding of reality. It states that the laws of physics are identical for everyone, regardless of their motion. This idea deviates from our everyday experience, where we assume that adding speed to something already moving makes it faster. Instead, Einstein's theory asserts that there is a maximum speed. Nothing can exceed the speed of light. From this perspective, events that seem simultaneous to us may not appear that way to someone moving near the speed of light. Another result of this new way of thinking is length contraction. If something is moving, it appears shorter in the direction of motion when observed from a stationary position. The famous equation, derived from special relativity, demonstrates how energy and mass can be converted into each other. This is crucial for understanding how tiny particles behave at high velocities and for processes like nuclear reactions. Special relativity is not just a theoretical concept. It has practical applications in modern technology, such as GPS. When GPS satellites send signals to your device, they are moving, so time behaves slightly differently for them. Without accounting for this time dilation effect, GPS calculations would be inaccurate. Einstein's general theory of relativity, introduced in 1915, delves deeper into the connection between gravity and the structure of the universe. It overturns the old idea that gravity is merely a force that pulls objects from a distance. Instead, It explains that gravity exists because spacetime itself is curved or warped. Imagine spacetime as a large, stretchy fabric. When a massive object like Earth is placed on it, it creates a dent. Smaller objects like balls roll towards the dent. This describes how objects move due to gravity, not as a mysterious force, but as a natural response to the bending of spacetime. Understanding general relativity requires imagining the universe as a four-dimensional entity, combining 3 dimensions of space with one of time. Massive objects such as stars, planets, and even us influence how spacetime is shaped around them. One pivotal moment that confirmed the accuracy of general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed near the sun. According to the theory, the sun's massive gravity would slightly bend the starlight. During the eclipse, their observations perfectly matched Einstein's predictions, solidifying the validity of his theory. The hypothesis suggests that much like movement can change how we experience time as per special relativity, gravity likewise influences time. Where gravity is very strong, time moves more slowly compared to regions with weaker gravity. So, if you were standing near a massive object like a black hole, your clock would tick more slowly than one set far away from the strong mass. General relativity introduces black holes, which are places where gravity is extremely intense. Inside a black hole, the gravitational force is so strong that nothing, not even light, can escape from it. The boundary around a black hole is known as the event horizon, and it acts like a point of no return. Once something crosses this boundary, it is pulled into the black hole with no chance of escape. Einstein's general theory of relativity has profound implications for how the universe is structured. Initially, he added something called a cosmological constant to his equations because he thought the universe was static. However, when it was discovered that the universe is expanding, he called this a colossal mistake. The idea of an expanding universe, based on general relativity, is a key part of the theory of the universe's origins, explaining how the universe began. Another significant concept from general relativity is gravitational waves. These are like ripples in the fabric of spacetime caused by massive objects moving rapidly, such as when black holes or neutron stars collide. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, confirming another aspect of Einstein's theory. Over time, scientists have conducted numerous experiments to verify general relativity, and each time it has proven to be accurate. Whether it's explaining how planets move, the bending of starlight, or detecting gravitational waves, the theory has consistently been supported by evidence. While suggesting that gravity is completely wrong might be surprising, especially since we all experience gravity daily. In physics, it's common to explore and debate different ideas. Scientists like Brian often challenge established theories. For instance, one alternative theory testing traditional gravity is called modified Newtonian dynamics, MOND. MOND proposes that gravity behaves differently at low speeds, especially in galaxies, without requiring dark matter. Instead of adding invisible matter, it suggests that gravity becomes stronger at low speeds. The debate about gravity also involves mysterious dark matter and dark energy, introduced to explain certain phenomena in space. Critics argue that these might not be necessary, and alternative ideas could explain what we observe. Some researchers who disagree with Einstein's theory of gravity explore other possibilities, such as theories involving unknown particles or forces that could modify or expand our understanding. It's important to note that in science, revolutionary ideas aren't dismissed outright. They are rigorously tested to see if they hold up. For instance, what Einstein described as time in four-dimensional space, where time travel into the past might be limited by the speed of light, has been creatively explored alongside concepts like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture suggests that time travel into the past is unlikely from a physics perspective. Ongoing experiments and observations aim to determine if new theories can explain phenomena like the strength of gravity, similar to what we already know. While alternative ideas have been explored, none have convincingly replaced the established principles of gravity. Questioning and testing ideas are critical parts of how science progresses, leading to further research and a better understanding of the universe. In the realm of gravity theories, general relativity remains the most significant and successful one. Despite challenges and alternative ideas, it consistently performs well in tests and explains various phenomena, such as how planets move and how light bends around massive objects. General relativity remains robust because it is both elegant and comprehensive, covering a wide variety of phenomena. As discussed earlier, Einstein's special theory of relativity suggests that time can behave differently depending on motion. Let's now explore what this idea means for practical applications, especially in space travel. Space travel is exciting yet challenging because space is vast, and according to Einstein's theory, the speed of light is the fastest anything can go. This creates enormous challenges for traveling between stars, even with advanced technology, due to the long timescales involved in reaching the nearest stars. Consider the famous twin paradox to understand how time behaves during space travel. Imagine one twin stays on Earth while the other travels to a distant star. When the space-traveling twin returns, they find that less time has passed for them than for their sibling on Earth. This means they have effectively traveled into the future. Time is crucial for space travelers because the longer the journey, the more time slows down for them due to time dilation. If astronauts travel to nearby stars, where time slows significantly, they could age more slowly than people on Earth. While this might seem like science fiction, it is a real effect predicted by the theory of relativity. Imagine sending a crew to a star system not too far away. Because of the immense distances involved, the journey could take many years, even at high speeds. For the astronauts on the spacecraft, time would feel slower due to time dilation, while much more time would pass on Earth. Time dilation affects not just living beings but also technology. Computers and communication systems on spacecraft must account for time dilation to ensure accuracy and proper functioning. Space travel at high speeds also involves. Could time dilation, as explained by Einstein's theory of relativity, make time travel into the future a reality for space explorers? Physical challenges such as prolonged isolation, exposure to cosmic radiation, and the psychological effects of being away from Earth for extended periods. In our daily lives, we can observe the effects of time dilation through the Global Positioning System, GPS. GPS relies on precise timing signals from moving satellites. Because these satellites experience time dilation, it is essential to account for these effects in GPS calculations. Failing to do so would drastically affect the accuracy of navigation systems. Now let's explore why time moves in one direction. Time governs our lives, moving from the past to the present and into the future. This one-way flow of time is fundamental to our existence. But why does time have this one-way nature? To understand, we look at entropy, a concept that measures disorder or randomness in a system. Entropy is tied to the arrow of time and tends to increase over time, making time flow in one direction. The second law of thermodynamics expresses this relationship, stating that in any isolated system, total entropy will either increase or, at best, remain constant. In simple terms, entropy naturally increases and does not decrease on its own. Understanding how things become more disordered helps explain the one-way flow of time. Imagine a neatly ordered deck of cards. If we shuffle them, they become messy and random. This transition from order to disorder demonstrates how time moves in one direction. This flow of time works differently at various levels. If we look at tiny particles, the laws of physics allow processes to move backward and forward in time, a concept known as time reversal symmetry. The discrepancy between this and the irreversible changes we observe in the macroscopic world comes from initial conditions. The large, complex world we live in results from many particles interacting, creating a one-way arrow of time. This idea of time moving in one direction applies on a cosmic scale as well. The entire universe has been evolving in one direction since the Big Bang. The universe started in a state of low entropy, and over billions of years, it has become more disordered, forming galaxies and stars. Scientists are still trying to understand why the universe began in such an ordered state. Even in the small world of quantum mechanics, which deals with tiny particles, there is a time arrow. The way particles change over time seems symmetrical, but when we observe them, changes become irreversible. Brian suggests that it's not just a physics phenomenon. Our brains also experience time in one direction. We remember the past, live in the present, and think about the future in sequence. This mental arrow of time is tied to how we perceive the external world's arrow of time. This concept of time has significant philosophical implications, challenging how we understand reality. Time is a crucial part of how we experience life and make sense of the world. Without the one-way flow of time, everything would be entirely different.